Hi, this is Akash, and today I'm here to explain you transmission and distribution. Let's have a pre-test before starting the course. Hello everyone. Welcome back to the e-learning course on the part of power system basics that deals with transmission and distribution of power. In the previous part of the course, we have learnt about the generation of power. In this part of the course, we are going to deal with the transmission and distribution of the generated power. This transmission and distribution course is further divided into two parts. In this course, we are doing the first part of transmission and distribution. So, let's get started with the course. Have a look at the course objectives. By the end of this course, you will be able to list various advantages of DC and AC transmission system. Explain about types of bus bar configurations. Explain about role and features of transmission line. List various transmission tower types and designs. Explain about constants of overhead transmission line. Define transmission efficiency. Define transmission line voltage regulation. Define sag in overhead conductors. List two ways of transmission of electrical power. Now, let us discuss about the electrical power transmission system. Fundamentally, there are two types by which electrical energy can be transmitted. High voltage DC electrical transmission system. High voltage AC electrical transmission system. Click on each tab to learn more. The first one is high voltage DC electrical transmission system. These are the advantages of it. Only two conductors are required for DC transmission system. It is further possible to use only one conductor of DC transmission system if earth is utilized as return part of the system. The potential stress on the insulator of DC transmission system is about 70% of same voltage AC transmission system. Hence, less insulation cost is involved in DC transmission system. Inductance, capacitance, phase displacement and surge problems can be eliminated in DC system. The second type of system is high AC electrical transmission system. These are the advantages of it. The alternating voltages can easily be stepped up and down, which is not possible in DC transmission system. Maintenance of AC substation is quite easy and economical compared to DC. The transforming of power in AC electrical substation is much easier than motor generator sets in DC system. This table gives you the information about types of power transmission system used based on voltage levels. Have a look at the table. Now our next topic is about bus bar configurations. Different bus bar schemes or configurations are used in different types of substations to suit the requirement of the stations. The physical size, type and arrangement of major equipment such as power transformers, circuit breakers, isolators, current and voltage transformers, etc. may cause variance in the layouts. It is important to design a flexible bus bar arrangement so that power may be served through alternative arrangement during fault in any specific substation equipment. The equipments can be attended and maintained without any supply interruption during routine and breakdown maintenance. There are different types of bus bar configuration which are discussed further. First type of bus bar configuration is single bus bar configuration. A single bus bar configuration consists of one main bus that is energized at all times and to which all circuits are connected. This is the simplest arrangement and provides least amount of system reliability. These bus configurations are used in small distribution substations where reliability of service may be compromised. Click on each tab to learn more. Its advantages are lowest cost, small land area required, relatively simple for the application of protective relaying. Its disadvantages are single bus arrangement has the lowest reliability. Failure of a circuit breaker or a bus fault causes loss of the entire substation. Maintenance of one circuit necessitates de-energizing or protection of the other connected circuits to the bus. Next type of bus bar is single bus bar with sectionalized configuration. An extension of the single bus configuration is the sectionalized bus arrangement. This arrangement is basically two or more single bus schemes and each tied together with bus sectionalized breakers. The sectionalized breakers may be operated normally, open or closed depending on system requirements. In this arrangement, a bus fault or breaker failure causes only the affected bus section to be removed from service, thus eliminating total substation shutdown. Click on each tab to learn more. It has the following advantages: higher reliability than single bus scheme, isolation of bus sections for maintenance, loss of only a part of the substation for a breaker failure or a bus fault. Disadvantages are a sectionalized bus arrangement has an extra circuit breaker leading to increased cost of this system. Additional circuit breakers are required for sectionalizing. Next type of bus bar is main and transfer bus configuration. The main and transfer bus configuration consists of two independent buses, one of which the main bus which is normally energized. Under normal operating conditions, all incoming and outgoing circuits are fed from the main bus through their associated circuit breakers and bay equipments. If it becomes necessary to remove a circuit breaker from service for maintenance or repair, the integrity of the circuit operation can be maintained through use of the bus tie bay as shown in the figure, thus ensuring reliability of service. Click on each tab to learn more. Its advantages are accommodation of circuit breaker maintenance while maintaining service and line protection, reasonable in cost, fairly small land area required compared to the flexibility achieved. Disadvantages are an additional circuit breaker is required for bus tie, since the bus tie breakers have to be able to be substituted for any line breaker. Its associated relaying may be somewhat complicated. Next type of bus configuration is 1.5 breaker bus configuration. 1.5 breaker configuration consists of two main buses which are normally energized. The two buses are electrically connected with three circuit breakers, with a circuit coming out between each two breakers. In this arrangement, as three circuit breakers are used for two independent circuits, hence there are 1.5 circuit breakers per circuit. In this arrangement, better reliability and flexibility is attained during operation and maintenance. Faults on either of the bus do not cause any interruption. Click on each tab to learn more. Its advantages are as follows: flexible operation, high reliability, can isolate either main bus for maintenance without disrupting service, can isolate any circuit breaker for maintenance without disrupting service, double feed to each circuit. Bus fault does not interrupt service to any circuits. all switching done with circuit breakers. Disadvantages are 1.5 breakers are required per circuit. Relaying is involved since the center breaker has to respond to faults of either of its associated circuits. Land requirement is more. Next type of bus configuration is double bus configuration. The double breaker double bus configuration consists of two main buses energized, and the buses are electrically connected with two circuit breakers with one outgoing circuit between the two breakers. In this configuration, two circuit breakers are required for each circuit, and any circuit breaker can be removed from service without interruption of the other. Faults in either of the main buses also do not cause any interruption. This configuration is usually limited to large generating stations because of high cost, which can afford this additional reliability. Click on each tab to learn more. Its advantages are flexible operation, very high reliability, isolation of either main bus for maintenance without disrupting service, isolation of any circuit breaker for maintenance without disrupting service, double feed to each circuit, no interruption of service to any circuits from bus fault, all switching with circuit breakers. Its disadvantages are this configuration carries a high cost. Two circuit breakers are required for each circuit. Next type of bus configuration is double bus bar with bypass isolator scheme. It is a combination of double bus and main and transfer bus schemes. It is used by some utilities for 400 kV and 220 kV substations. Click on each tab to learn more. Its advantages are most flexible in operation, simple operation, highly reliable. Either main bus can be taken out of service for maintenance. Its disadvantages are high cost. Next type of bus configuration is mesh ring scheme. It is used by very large power stations having large number of incoming and outgoing lines. It is unsuitable for a developing system. Click on each tab to learn more. Its advantages are provides double feed to each circuit, permits breaker maintenance without interruption of supply. All sections of conductor and substation are covered by the feeder protection and no separate bus protection is required. Cheaper than double bus or main and transfer bus schemes. Its disadvantages are protection is complex. This is the image of a transformer from a yard. The box that is present on the left side is the transformer. These are the brushings, the conductors from which are connected to the circuit breakers. We can see the three circuit breakers for the three phases, that is R, Y and B. These are further connected to the isolators. Next topic that we're discussing about is transmission line. Transmission line is the long conductor with special design bundled to carry bulk amount of generated power at very high voltage from one station to another as per variation of the voltage level. This is how transmission line looks like. Following are different transmission tower types and their designs. 115 kV wood edge frame, average height 65 inches, average span 750 feet. 115 kV improved appearance double circuit, average height 70 inches to 90 inches, average span 350 to 900 feet. 115 kV steel lattice, average height 75 inches, average span 1150 feet. 230 kV wood edge frame, average height 70 inches, average span 750 feet. 230 kV steel lattice, average height 85 inches, average span 1150 feet. 230 kV steel lattice double circuit, average height 120 inches, average span 1150 feet. 230 kV improved appearance, average height 110 inches, average span 900 feet. 230 kV improved appearance double circuit, average height 115 inches, average span 900 feet. 500 kV lattice, average height 135 inches, average span 1150 feet. 500 kV lattice, average height 125 inches, average span 1150 feet. 500 kV steel lattice double circuit, average height 170 inches, average span 1150 feet. 500 kV improved appearance double circuit, average height 170 inches, average span 1150 feet. This is the typical conductor arrangement. This is the shield wire or earth wire. These are the phase conductors. This is the protection angle. These are real-time images of transmission tower. This is the 400 kV transmission tower arrangement. This is the sketch of it and this is the real-time image. This is the 765 kV transmission tower arrangement. This is the sketch of it and this is the real-time image. This is the 1200 kV transmission tower arrangement. This is the sketch of it and this is the real-time image. Following are the points that to be considered for designing transmission tower. The minimum ground clearance of the lowest conductor point above the ground level. The length of the insulator string. The minimum clearance to be maintained between conductors and between conductor and tower. The location of ground wire with respect to outermost conductors. The mid-span clearance required from considerations of the dynamic behavior of conductor and lightning protection of the line. A transmission line has resistance, inductance and capacitance uniformly distributed along the whole length of the line. Before we pass on to the methods of finding these constants of a transmission line, it is profitable to understand them thoroughly. Click on each tab to learn more. It is the opposition of the line conductors to current flow. The resistance is distributed uniformly along the whole length of the line as shown in figure 1. However, the performance of a transmission line can be analyzed conveniently if distributed resistance is considered as lumped as shown in figure 2. This is equation for resistance. When an alternating current flows through a conductor, a changing flux is set up which links the conductor. Due to these flux linkages, the conductor possesses inductance. Mathematically, inductance is defined as the flux linkages per ampere. That is, the inductance is also uniformly distributed along the length of the line as shown in figure 1. Again, for the convenience of analysis, it can be taken to be lumped as shown in figure 2. This is equation for inductance. We know that any two conductors separated by an insulating material constitute a capacitor, as any two conductors of an overhead transmission line are separated by air which acts as an insulation. Therefore, capacitance exists between any two overhead line conductors. The capacitance between the conductors is the charge per unit potential difference, that is, the table shown above gives indicative values of inductance and capacitance per unit length corresponding to a given voltage level of transmission line. It also shows the S impedance, surge impedance, SIL, megawatt, surge impedance limited, and TH limit megawatt threshold limit for a given transmission line voltage. Now let's learn about different types of transmission line. In transmission line determination of voltage drop, transmission efficiency, line loss, etc. are important things to design. These values are affected by line parameter R, L and C of the transmission line. Lengthwise transmission lines are of three types. Click on each number to learn more. Short transmission line. Length is about 50 km. Voltage level is up to 20 kV. Capacitance effect is negligible. Only resistance and inductance are taken in calculation. Capacitance is neglected. Medium transmission line. Length is about 50 km to 150 km. Operational voltage level is from 20 kV to 100 kV. Capacitance effect is present. Distributed capacitance form is used for calculation purpose. Long transmission line. Length is more than 150 km. Voltage level is above 100 kV. Line constants are considered as distributed over the length of the line. Transmission efficiency is defined as the ratio of receiving end power PR to the sending end power PS, and it is expressed in percentage value. It is given by the formula cos theta S is the sending end power factor, cos theta R is the receiving end power factor, Vs is the sending end voltage per phase, Vr is the receiving end voltage per phase. Voltage regulation of transmission line is defined as the ratio of difference between sending and receiving end voltage to receiving end voltage of a transmission line between conditions of no load and full load. It is also expressed in percentage, where Vs is the sending end voltage per phase and Vr is the receiving end voltage per phase. XL is the reactance per phase. R is the resistance per phase. Cos theta R is the receiving end power factor. Effect of load power factor on regulation of transmission line for lagging road, for leading road. Sag is defined as the difference in level between points of supports and the lowest point on the conductor. Sag is mandatory in transmission line conductor suspension. If the conductor is stretched fully during installation, wind exerts pressure on the conductor. Hence, conductor gets chance to be broken or detached from its end support. Thus, sag is allowed to have during conductor suspension. These are the sag calculations for support, which are at equal level. Suppose AOB is the conductor, A and B are points of supports. Point O is the lowest point and midpoint. Let L is equal to length of the span, that is AB. W is the weight per unit length of the conductor. T is the tension in the conductor. We have chosen any point on conductor, say point P. The distance of point P from lowest point O is x. Y is the height from point O to point P. equating two moments of two forces about point O as per the figure above we get. These are the sag calculations for support which are at unequal level. So having calculated the value of x1 and x2, we can easily find out the value of sag S1 and sag S2. So having calculated the value of x1 and x2, we can easily find out the value of sag S1 and sag S2. The above formula are used to calculate sag when the conductor is in still air and ambient temperature is normal. Hence, the weight of the conductor is its own weight. There are two types for electrical power transmission. Click on each tab to learn more. Overhead transmission. Bare conductors hanging from the supports. Porcelain insulators to insulate the conductor from the support. Less costly. Prone to occurrences of faults. Less time required for repairs. Underground cables. Used if overhead transmission is not feasible. Insulated conductors. Very costly. Less likely to develop faults. Long repair time in case of faults. Can be used in river crossings, large road crossings, and in dense urban areas where aesthetic issues are important. Besides economics, there are some technical reasons for unpopularity of underground cables. Line charging current is 20 to 75 times that of overhead transmission. The following table gives the representative value for charging current corresponding to various voltage levels and length of transmission lines. 345 kilovolt cable, 5 miles. Charging current 145.2 ampere. 345 kilovolt overhead line, 100 miles. Charging current 160.48 ampere. 765 kilovolt overhead line, 150 miles. Charging current 492.9 ampere. Charging current may be as high as the line capacity for long cables. For 345 kilovolt lines, no power can be transmitted if length becomes 26 miles. For 230 or 345 kilovolt, limiting length is 20 miles. Following are the properties of overhead conductor. Conductor is a physical medium to carry electrical energy from one place to other. Corona is ionization of air due to higher voltage, usually voltage above critical voltage, which causes violet light around the conductor and hissing sound. It also produces ozone gas, therefore it is undesirable condition. The choice of conductor depends on the cost and efficiency. An ideal conductor has following features. It has maximum electrical conductivity. It has high tensile strength so that it can withstand mechanical stresses. It has least specific gravity, that is, weight or unit volume. It has least cost without sacrificing other factors. There are different types of overhead conductors. Click on each tab to learn more. IACS, International Annealed Copper Strand. It is 100% pure conductor and it is standard for reference. AAC, all aluminium conductor. It has lesser strength and more sag per span length than any other category. Therefore, it is used for lesser span, that is, it is applicable at distribution level. It has slightly better conductivity at lower voltages than ACSR, that is, at distribution level. Cost of ACSR is equal to AAC. ACAR, aluminium conductor, aluminium reinforce. It is cheaper than AAC but prone to corrosion. It is most expensive. AAAC, all aluminium alloy conductor. It has same construction as AAC except the alloy. Its strength is equal to ACSR, but due to absence of steel, it is light in weight. The presence of formation of alloy makes it expensive. Due to stronger tensile strength than AAC, it is used for longer spans. It can be used in distribution level, that is, river crossing. It has lesser sag than AAC. The difference between ACSR and AAAC is the weight. Being lighter in weight, it is used in transmission and sub-transmission where lighter support structure is required, such as mountains, swamps, etc. ACSR, aluminium conductor steel reinforced. It is used for longer spans, keeping sag minimum. It may consist of 7 or 19 strands of steel surrounding by aluminium strands concentrically. The number of strands are shown by X, Y, Z, where X is the number of aluminium strands, Y is number of steel strands, Z is diameter of each strand. Strands provide flexibility, prevent breakage, and minimize skin effect. The number of strands depends on the application. They may be 7, 19, 37, 61, 91 or more. If the aluminium and steel strands are separated by a filler such as paper, then this kind of ACSR is used in EHV lines and called expanded ACSR. Expanded ACSR has larger diameter and hence lower corona losses. This is the image of 5-layered stranded conductor. Bundle conductor. For extra high voltage lines above 220 kV, more than one conductor are used in each phase. Such bundle of conductors 2, 3, 4, 5, 6 per phase helps in reducing the potential gradient at the conductor surface. This helps in reducing corona effect. Bundle conductor lines have increased effective radius called GMR, geometrical mean radius. Besides corona reduction, other effects are reduced series impedance, increased power transfer capacity compared to the line having the cross section of the solid conductor of the same conductor volume as the bundled conductor. We have come to the end of this module on power system basics, which covered the leading part of transmission and distribution. Here is a quick recap of the key points discussed in this module. In this module, we have learned advantages of types of transmission system, bus bar configuration and its types, transmission lines and their role and features, various types and designs of transmission tower, constants of overhead transmission line, transmission efficiency and its equation, transmission line voltage and its equation, sag in overhead conductors, 2 ways of transmission of electrical power. Thank you for your time. Hope you enjoyed learning. Click Next to take the post test.